Thanks.
Good afternoon, everyone. Welcome back. Our next speaker is Miguel Miranda, George Miguel Alberto de Miranda, Executive Director of Atlantic International Research Center, President of the Portuguese Institute for the Sea and the Atmosphere from 2013 to 2023, full professor at the University of Lisbon. He has held and still holds several leading positions in international organizations in his scientific area. He has directed several academic and scientific organizations and developed research activity in geomagnetism, marine geophysics, and natural hazards. He is the author or co-author of 100+ indexed articles published in main scientific journals of geophysics. He is Vice President of Science class of the Lisbon Academy of Sciences. Sir Miguel.
Hello, Priyanka. Thank you for the presentation. It could be synthesized in a single sentence. I'm old. And being old means that. That means that we have lots of experience for different situations. In the recent decades, I would say I've been managing research-based institutions. And that's how I arrived to the Air Center. First of all, I must thank all of you to be here. This is an initiative that is promoted by the Air Center since 3 years, I think. 4 years. But you know, before I came in, there was no Air Center. This is a joke, of course. We make an effort, a significant effort to make this possible. We have support from several entities, but it is very important for us that we are able to cultivate, to maintain the community even in the times we are living that are very difficult, especially for the transatlantic relationships. All of you have TV, so I do not need to make any kind of details, but I must tell you that one of the big advantages of geosciences, in the same sense, JuliaEO is related with geosciences, is that the Earth is a single one, and we are able to keep cooperation even in war times, even in very difficult times. What shall people ask from all of you? Outcomes. Outcomes from this effort that will support the living and the life and wealth of normal people. Understand that we are here to work for the citizens in the different communities. We have no distinction on continents, on countries, on communities. We have only one goal is to promote and to share knowledge and to use the best knowledge available to be able to organize the most relevant, I will say, services that can be given or made available to a normal citizen anywhere, from a small beach in the south of Africa to a big metropole in the south of America. So let's try to keep transatlantic ties strengthened, strong, and let's not take too much effort on the espuma dos dias, anything, something that seems very important today, it will be forgotten tomorrow. It's only ersatz. Let's forget it and concentrate on what we are able to do and what we know how to do it. That is modeling the Earth system in the different subdomains, use the best available IT tools to do this kind of modeling, share knowledge freely and openly with everyone, and be a part of what will be the future, despite what will happen in forthcoming days. So, thank you very much for your patience.
Thank you, sir. Our next speaker is Avik Sen Gupta. Avik Sen Gupta is the VP of Engineering at Julia Hub, where he is responsible for building their cloud compute and simulation platform. He is a contributor to Julia and maintainer of several Julia packages, as well as the author of Julia High Performance. Avik, sir, has previously created complex trading systems for the world's leading investment banks.
This is connected, but it's not showing up there. This is connected,
It is.
but that's showing something else. That's not mine.
Exactly.
That's not mine.
So this image is not from your laptop?
No, no. It is nice, but not mine.
Northern Lights, no?
Yeah.
I'm a geomagnetician.
So maybe it's yours, but not mine. It's coming from somewhere else. Also, it says 427, so that's not mine either.
Could you unplug and plug again?
My computer has an external display connected, so
Could you unplug it and plug it again?
yeah. Yeah.
Experimenta este. Às vezes
No, this has a second screen, so this is connected to something, but that's not.
it is.
É assim, eu ali estou a recebê-lo. O que está no coisa, no ecrã.
I did test it.
É, o projetor ele está a ler o dele. Muda aí HDMI 1, acho eu 2, vê lá. Ok.
Yeah.
Wait. ser uma. Demora um bocadinho.
Yes,
Ok.
that is mine,
Ok.
I think. Yes. Thank you. There we go. Thank you for inviting me. Lovely place, lovely day. And my name is Avik Sengupta. As I work for Julia Hub. I've been with Julia Hub for a while now. And today I'll talk about using Julia, deploying Julia to other people, right? Other machines, other people, other places. So hopefully, it'll be something that people care about. A little bit about why, to give you a background on some of the things I will say. It comes from my experience writing Julia for the last 10, 12 years. And I say this not to, brag, but to say that many of the things that I'll talk about today is changed over the last 10 years, right? So when we started, there was a lot of things I talked about didn't exist. Maybe even 5 years ago, if I would have done this talk, it would have looked very different. So things keep changing. Thank you. So among the topics that I'll talk about today, we'll talk about packaging, how to package Julia code to ship to other people. We'll talk about sysimages and therefore package compiler.jl. I'll briefly touch about Julia C, and throughout my talk, I'll mention sort of caveats, tips, tricks, stuff that we have learned that makes little things that make a big difference in when you are shipping Julia to production machines, really. The first thing I wanted to mention is that when we say deploying Julia, it means different things to different people, right? You could be deploying to local clusters. You could be deploying to AWS. You could be deploying to your colleagues' workstations. You could be deploying different things. You could be deploying batch processes that are run on demand, that somebody runs a simulation on that takes an hour or 6 hours or 2 days. You could be developing web services that are servicing requests from public customers. You could be deploying a desktop UI, right? And that's possible in Julia. Imagine that. You could be deploying open source code. You could be deploying internal code within your organization. You could be deploying, building commercial projects that you send an installer to your customers to run, right? And all of these have different requirements, different needs. And so I think one of the primary messages I want to do today is there are many things you can do. Try to find the simplest thing that solves your problem, right? A lot of discussion around deploying in Julia will talk about, package compiler or sysimages or even Julia C today. But do you really need it? Maybe not. So think about that. So given all this variety of users, I want to sort of abstract it out into the topics that I'll speak about for the next few minutes. And the way I look at deployment is running code in a machine that you don't own, that you haven't developed on, right? That's I think the key sort of differentiator that you need to think about. And the reason why you need to think about that is that every piece of code that you write always has implicit dependencies and assumptions about where it was developed and how it was run. So certainly obvious things like operating systems, but also the instruction sets, not just ARM versus x86, but even in x86, the instruction sets, the actual CPU features that you have, the libraries that you depend on, right? And there are multiple layers to that, to library dependencies, and we'll see some of that as we go along. Even the configuration files, right? The data sets that you depend on. And you have to think about all of these things as you deploy, right? And the important thing is to sort of enumerate them, have an answer to each of these problems as you are deploying, right? So the simplest thing that you could possibly do, of course, is write your code in a Julia file, a .jl file, and email it to somebody, right? And that works, right? And I'm sure a lot of you have done that in the past as you have written Julia code. The problem, of course, is that the user needs Julia installed, but also the user needs all the Julia dependencies installed. And that gets to be the biggest problem, right? Do they have the correct version of http.jl or, and that's a big problem that you need to solve, right? So this solution of emailing Julia files works, but only for simple code, for somebody that your colleague who can walk over and debug together. That's the use case where that'll work. But very soon it falls apart, right? So the next thing that you can do, and this is probably one of the widest use cases that you can do, is to not just send your source code, but also to send a project and a manifest with it, right? So every Julia package comes with a project toml, which, for a package, you should check it in to Git, obviously. I would recommend that for applications, so for the final thing that the user runs, you also check in the manifest, right? For libraries, you shouldn't check in the manifest, but for end user applications, you should check in the manifest. And given a project and a manifest, you are guaranteed that your user has the same versions of dependencies, right? Of Julia packages as dependencies. And so that gives a much greater guarantee that the code will run successfully. The trouble, of course, is that the user needs to still install the correct version of Julia. And you can, maybe a minor patch version doesn't matter, but something that you have tested with Julia 1.12 certainly won't run on another machine with Julia 1.11, right? There is some functionality in JuliaEO that's coming that will help with that, where JuliaEO can actually read the version from a manifest and then run the correct version of Julia for you, right? And that'll, help in this regard, right? One of the big advantages of sending up the source code with the project and the manifest is that you don't need to worry about operating systems, right? The same package will work for Mac, Linux, or Windows, and the user will just instantiate it, right? One downside is, of course, you're now having to track multiple files, right? You have to zip up your source code, the project toml, manifest toml, put them into version control and all of that. But in 1.13, actually, you can store a project toml and its manifest within a source code. And that's, not in 1.12 yet, but in 1.13, that'll, this idea of just sending out source file with a project embedded in it will actually start working from 1.13. So I think this, the simplest way of sharing Julia code, which is Julia source code with a project and a manifest, actually probably works in a lot of cases, right? So try this first before doing everything else that I'm talking about for the rest of this talk, right? Right. One recommendation that I always say is that if you're writing private code, unless you are one developer installing on one machine, always create a registry for your organization, for your team. It's not very difficult. It's just a Git library, a Git repository. There are tools that can help you with it. Local registry works pretty well. For larger companies, obviously, JuliaHub sells a solution, but for reasonable sized teams, you don't need any of that. Local registry is really good. All the tooling that General uses is available open source, so you can use sort of validations that General registry does. You can do it for your private registry, and it helps immensely in keeping track of what versions you are using. Otherwise, you very easily just lose track of what version which machine has, right? So always use a registry. If you're doing this on HPC clusters, you have a few extra considerations that you should think about. First is that, obviously you need a depot that all your nodes can use, right? So they should be picking up the code and the compiled code from a single place. So you should set up a depot to a shared file system. Typically, shared file systems are slow on clusters, so try to find the fastest one. Maybe a temp. Sometimes the temp shared systems are faster than home directories, so try to use that. The important thing on a large cluster is that you should always pre-compile before you run your job, because we've often seen that you run on 1,000 node, all those 1,000 nodes start compiling your code simultaneously, and then they are writing to a shared depot, everything just breaks, right? If you can pre-compile on a login node and then run your job, there's a Julia command line option called minus compile module strict, which will fail unless everything is pre-compiled already, right? So any distributed job you start, if you start with this compile module strict, then you are guaranteed that you have pre-compiled it before the job start. Otherwise, the job fails. And that's very useful, because otherwise, as I said, if 1,000 nodes start compiling Julia code simultaneously, you don't want to spend the electricity cost for that, really. That's terrible, right? If your cluster has heterogeneous nodes, you should worry about the CPU target that you set for pre-compilation. So you need to, and we'll talk a little bit more about that. And the final thing on a large cluster is, of course, MPI config, which I have no idea about, but you should ask somebody how to set it. And that's something that is probably one of the most complicated things that you will do on a cluster running Julia code, right? Right. Often, you will package your code into a Docker container, and that's very useful. There are public Julia Docker images that are available, which are pretty useful. You should always build on top of that. The important thing, again, is to pre-compile during Docker build time, right? Which means you need internet access during Docker build time. You need to worry about what machine you are doing your Docker build, because, again, CPU targets matter. So, if the machine that you're doing your Docker build is not the machine on which you will run things, you need to set your CPU target. This is sort of the default CPU target that works across all machines, so use that. On Docker, one of the things that happens is that Julia's garbage collector figures out how much memory is there on the machine and decides when to run, depending on how much memory there is in the machine, right? It doesn't only look at the memory that your program is using, it also looks at the memory that is available on the machine, right? If you're running Docker on a larger host, then Julia looks at the memory of the host, not of your Docker container, right? And so you can mitigate that by setting a heap size, saying, Julia should only use a certain amount of heap, which is what your Docker container is set to, rather than the host memory, right? Similarly, your Docker container will have a number of virtual CPUs that are different from the host, and so you should also set the thread limits correctly when you're running code inside Docker, right? And aside on precompile workload, I've talked a couple of times about the fact that you should use precompile. Realize that Julia precompiles code that only runs at compile time, right? So that the code that is at the top level of your module, that is the only code that Julia will precompile. So if you have a function that takes a long time to compile and that doesn't run when the compilation step happens, that function won't be compiled. And then when you run it, it'll compile it and it'll take 30 seconds and you'll be back where you started, even though you have precompiled it. So think about your precompile workloads, and there are tools to help you do that, manage that. There's precompile tools, or you can just manually put those function calls at the top level with some dummy data, and that works as well. But think about that as you are packaging things. Now, so all of this was just ship your code, ship source code, precompile at build time, and off you go, right? Sometimes that's not enough, and sometimes you will hear people talk about system images. A system image is basically a snapshot of memory of a running Julia session. So it contains compiled code, native compiled code, and it loads faster than, loading a PKG image or a standard precompiled image, right? Custom sysimages basically solve the latency, the compile time latency, the first run latency. So for example, modeling toolkit on my machine takes maybe 5 to 10 minutes to precompile. And even after precompiling, the first using for modeling toolkit can take anywhere between 3 to 10 to maybe sometimes 30 seconds, right? Even after precompiling. So sysimages solves this problem. And to build sysimages, there's a tool called packagecompiler.jl, which does that for you essentially. That's all that it does. So it's a Julia package, you install it, you say using package compiler, and then it has a function called create sysimage, right? So here I'm creating a sysimage with the modeling toolkit and JLMaki, which are two of the Julia packages which probably have the longest compile times. And then when you load that sysimage using this -- sysimage command line flag to Julia, Julia loads up as it normally does, and then using modeling toolkit now is pretty much immediate, right? And that's basically what you get by using sysimages. That your first run latency is significantly reduced. But it's not free, right? It does reduce compile time latency, but do you really need to reduce compile time latency? In many use cases, you don't care about first run latency. But in cases where you do, it helps a lot. It still needs a C compiler on your build machine. On Windows, it automatically installs it, so that's easy. You still need the same version of Julia to load it that you used to create it. You need to download artifacts. So, you need all. So if you have, like modeling toolkit has the solvers have Fortran code that are, compiled into DLLs or SOs. You need to somehow get that as well, right? You don't really need the sources, but given the sysimage, if you are trying to do any package operations, you're trying to add more packages on top of your sysimage, you will still need the sources for the packages that you build. So if you are, creating a sysimage from proprietary code, and that, sort of obfuscates your code a little bit, that works. But if you want your user to add a new package on top of your sysimage, you need to think about what you can do. The biggest problem is with a sysimage is it takes a long time to build. It takes 20, 30, maybe hours to build large sysimages. And it creates humongous files, right? So, 2 GB is very easy. There's a 2 GB sysimage limit in Windows in Julia. There used to be a 4 GB limit on Linux. Maybe that's been fixed, I don't remember. But, you hit these limits very quickly where those sysimages are really, really big. So there is a downside to using sysimages, even though, you solve the package everything together problem and you solve the latency problem, right? One of the additional things you can do with a package compiler is to bundle everything, right? As I said, with a standard sysimage, you need the Julia, you need Julia installed, you need the artifacts, so you need all your native dependencies. But package compiler also has a create app command that can basically bundle everything. So it'll bundle Julia, all your artifacts, and the code that you have written into a sysimage and bundle all of that into a directory which you can just zip and send, right? And that helps a lot in the packaging problem, right? This is even bigger. So, if your sysimage is like 2G, this will be 2.5G with all the, maybe we actually have 8 gigs of bundles for some of our products with, it'll have MKL, which is a gig, and it'll have CUDA, which is another gig. And so these are humongous file sizes, right? One thing to remember as you are using sysimages is relocatability, right? When you have a sysimage, your code is not being loaded from the Julia depot. So it's not being loaded from .julia/packages, right? So any code that has dependencies about where it's loaded from will fail. And so, when sysimages sort of came into being, sort of 3-4 years ago, there was a huge effort across the ecosystem to actually go and fix packages that had these assumptions. For example, timezones.jl for a long time didn't work with sysimages because it would load the time zone files from its source code directory, which obviously doesn't exist with a sysimage. So you need to think about, how you're loading stuff. Do you have sort of file paths or global pointers in your module globals? So you need to get rid of all of that and use either init or once per process to handle all of that, right? Right. So sysimages create large binaries, and obviously the solution is to create small binaries, and that is what JuliaC is all about. And JuliaC, there's a whole lots of videos. JuliaCon talks about JuliaC, so I won't go into too much detail. The big thing with JuliaC is that currently we can create binaries which are about 1.5 meg, right? And it'll go down even smaller. The downside is that all the code that you use with JuliaC needs to be statically inferable, right? So you can't use any dynamic dispatch, and that is your code and all your packages code, right? So as I said, when sysimages came in, we went through across the ecosystem of Julia packages to clean things up, to not have any file path dependencies. We now need to do the same across the ecosystem for JuliaC, right? Because a lot of packages depend on dynamic dispatch. And so a lot of base has already been cleaned up, but as you start using http.jl, for example, you will find that there is a lot of dynamic dispatch, right? So the key innovation of package compile of JuliaC is basically what is called trim support in the compiler, which takes your code, runs your infers your code, and figures out all the dependent functions that you will call from your code, right? And then it removes everything from the standard libraries, from all the dependencies, and just creates a binary with everything that you will actually call, right? And that is in the compiler, but you need some infrastructure around it, and that infrastructure is run using a application called JuliaC, which you can add, right? Sorry, yeah. So you can in Julia there's a new command called application add or app add. You say app add JuliaC, that gives you a command line on your machine called JuliaC, obviously, and you call JuliaC on a Julia package. In this case, I'm calling it on a package called hello app, which has one file, and you say output exe, and then you say -trim, right? And that will trim it, and that creates a small binary called hello. You run it, and that that's about, as I said, 1.5 MB, and it runs. It's a completely standalone binary, right? But when I say standalone, I'm sort of lying a bit because it actually depends on libjulia, which is sort of the underlying Julia runtime, right? So if you do, if you look at the dependencies of this binary, you will see that it depends on, libjulia.so and libjuliainternal.so, and also all of its dependencies like libunwine, which is a Julia dependency. So you still need this installed at some point in some way, right? Or you need to, somehow get these libraries onto your target machine, right? But JuliaC has an option to that. You can do what is called packaging or bundling. So if you say JuliaC ---- bundle, that will then actually just put your code, the binary, which is hello, and all the dependencies of Julia, and it'll just create it in a single directory, and everything will be sort of pointed at the relative file path, right? So that's JuliaC. How am I doing for time? Okay-ish, I think. Right? Okay, So that's, as I said, there are lots of videos on JuliaEO on the internet. There is documentation, so, there's a lot to be said about that. But for now, if you have code that is fully inferable, then JuliaEO is a good option for distributing it. And, there's a lot of work going on to actually make JuliaEO create sort of embeddable, so, on a low power embeddable machine. And, so people are using JuliaEO to take Julia code and put it on, a small device, which is, part of a satellite or a car or whatever, right? All of that is being worked on, right? Shifting gears a bit for the last few minutes. If you're running long-running services, web apps, API endpoints, you will do your precompile, you will start your Julia process, but your first request will still hit a function that, have you compiled it or not, right? So you need to worry about what happens when your first request comes in. Does the function that the request runs, has it been precompiled? Is it part of your precompiled workload, right? So, I was talking about precompiled workload before. This is also one area, if you're running a service, you need to think about it. If if precompiled workloads are too complex for you, then you should run warm-up requests, right? Bring your service up, have something hit all your endpoints one by one, and then open it up to your customers or to your clients. If you're running long-running services, you're presumably using http.jl. You need to think about what concurrency style you use, right? Threads or tasks or processes. http.jl can use one or all of them, depending on what your workload actually is, what kind of stability you need. You want to think about that. You need to think about a process manager, something that, Julia processes can crash. So you need to restart them. I would very much recommend not putting http.jl out on the internet, always fronted with, Nginx or Caddy or Apache or some more popular web server, primarily because http.jl is not that well tested for security issues, right? It's not that well used. So, you should pay attention to vulnerabilities. There is a new Julia vulnerability database that you should, follow if you are using http.jl in production, right? Finally, considerations for cloud native usage. If you're deploying to AWS or Azure, there are Julia packages for Azure and AWS that you can use to interact with the services. So, create new machines or secrets. You can do all of that. One thing about running Julia on the cloud is that Julia is generally more memory intensive than Python or Go. And memory is the biggest cost on the cloud, right? CPU is relatively cheap if you compare, with a local cluster versus AWS. CPU pricing is okay for, equivalent amounts of CPU, but memory is much more expensive. So if you're running Julia on the cloud, you have to think carefully about what, the economics of memory on the public cloud, much more than the economics of processors, right? Shared disks are slow again on the cloud, so think about that. Finally, Julia runs pretty well on Kubernetes, and there's a Julia package to manage Kubernetes processes. And I would recommend running, if you're running it on AWS, on Azure or GCP, try and figure out if you can run your processes on Kubernetes. That'll, make things easier actually. So on that note, questions, let me know. I'll be around for the next week. So happy to, go in more depth about any of these. Yes.
That's great presentation. Thank you so much. Mike's coming. So thank you so much for this great overview. It was really interesting. I have a question about JuliaEO.
Yeah.
So I have one packages which is essentially data loading packages.
Yeah.
It loads data, and depending on what type of the data is in the file, it returns a single precision or double precision array. So it is inherently type unstable because the type depends on what's on the disk. And so I'm considering to provide a separate API, a type stable API, where the user provides, okay, now I'm loading a double precision array. I know it's
Yeah.
double precision, so the Julia compiler can infer
Yeah.
now what's coming. And would this work with Julia C? So if a package has a type stable, unstable API, but this type unstable API is not exercised within a given program, would this still work with Julia C?
Yes, I believe so. I can't say with 100% certainty, but I am 90% certain it will work, provided that your precompiled workload, the trimming only happens based on your precompiled workload, and so when you're trimming, the path that it sees is fully inferable. Okay. It should work, right? Obviously, your users won't be able to call those other functions at runtime, but yeah, that should be fine, right?
Okay,
One thing I should also probably mention here is that there's a lot of I said for Julia C code should be inferable, right? And the immediate question that I asked Jeff immediately was, do you have a list of what it means, right? What is the definition of can you write down how to write code that will actually work? And generally the advice is that if the compiler says it works, right? So they're working a lot on making the error messages better. And so there won't be sort of a cheat sheet of how you write code, but you run the compiler on it, and the compiler will sort of tell you if your code won't compile with Julia C, and you fix it, right? And that's the workflow that people have been working on. There's also JET actually. So JET, which is a new sort of static analysis package, and JET should also tell you not 100%, but to a great degree of certainty whether your code will code is trimmable or not. And so you should run JET on your package actually. So in your CI, start running JET on your package, and then then you can keep it going to ensure that your package is Julia C compatible or trim compatible, right?
I have a second question, if I may
Yes,
ask.
sure.
I'm also interested in cross-compilation.
Yes.
So compiling Julia to WebAssembly or to another architecture, RISC-V, for example. And I use GPU compiler for that. And it works, but it's not a great fit because it's really specific to GPUs.
Yeah.
So is there maybe some time on the roadmap for Julia C to also support cross-compilation?
Yes, there is in the roadmap for Julia C to support cross-compilation. It's I know people are working on it right now, but it's going to be a lot of work, obviously. There's QEMU involved, and I think people are basically building a custom Linux distribution to allow cross-compilation to work. So yes, it's very much on the roadmap. It's being worked on today, but it'll take a while. But from the company perspective, our customers need it, and so we are working on it.
Well, I'll say that the cross-compilation that's kind of been planned is a little bit of a hack, because it's known that the cross-compilation in full is going to be extremely difficult to do, but we do have the binary builder infrastructure, and so what Jameson was proposing and putting out is tying Julia C with binary builder, so that way you can have basically run Julia C on VMs, and that gives you pretty much a good way to do cross-compilation in most systems. So.
Yeah. So yeah, not real cross-compilation, but effectively you just get a cluster to build everything for you.
Yeah.
Yes, true. But yeah, that's why I'm saying QEMU is involved, because right now Yggdrasil only sort of does it on fixed sort of CPUs, and so the idea with allowing this, because the reason why we want this from our point of view is to, as I said, compile to embedded systems, right? And so part of the work is to ensure that the Yggdrasil ecosystem can work for embedded operating systems and embedded machines, right? Yeah, you had a question?
Yeah, I had a question. Also regarding Julia C, I haven't used it yet, but it sounds amazing that you get it really small. I was wondering whether there is already now or maybe soon in the future a possibility for, say you have an application that consists of a couple of packages,
Yeah.
and you know that some of the kind of, let's say, the packages further down, that they're like static, and you don't actually need to, let's say, it will take a lot of time to compile through them,
Yeah.
but you know always exactly the types that go through them, so that's fine. So can you think of an application where you basically have it like two-layered, so you have it dynamic at the top, so that you as a developer, you can play around with stuff, but the stuff that you know is not going to change, you can just basically pass that to JuliaC, you can compile it, and therefore your playing around is kind of much quicker, because you still have the dynamic stuff at the top, but you have the advantage of the static compiler below.
So the detailed answer to that is probably a question for Jeff or Gabriel. So the one thing I can say that might help is the whole JuliaC infrastructure actually is also built to be embedded in Julia. So when you build something with JuliaC, there's a hack called --privatize now, where you can load the result back into a Julia runtime, right? So maybe that's something that you can use where, you load it back into so you have something that you compile with JuliaC, and then the result you load it back into a Julia REPL that is fully dynamic, right? And so, that kind of mechanism works. Maybe it needs better tooling, but that's one thing I can think of right now.
So what you basically propose ends up being how the actions for how the package binaries end up actually working in the latest iterations, right? So the neat thing is that is how package binaries are working. Now, the reason why you want to do that, though, the reason why you'd be asking it, though, is you say, oh, but package binaries you can't ship, but if I got this binary, I could potentially build this binary and then ship it to other people, right? That then comes into play with cross-compilation, right? So this is in the story of if we begin to start to have cross-compilation as part of the system, then we can start to think about things like, okay, maybe we build binaries for all these more static packages, like linear algebra packages and such, and we can ship the binaries to everyone. And so that you don't have to pre-compile on your own computer, you just get a binary just like you do for the rest of the binary builder system. But that's the limiting factor there is not the Julia infrastructure on how do I make this so that I can embed it back in Julia. The limiting factor there is all about cross-compilation, because otherwise it's like, oh, if I build it on this back, any binary that I get only works on this back, and so you need the ability to get all the different binaries easily.
So Jeff called this separate compilation, right? And this is very much on his roadmap. It has been on the roadmap for a while, but again, it's a huge amount of work. So that'll happen where, you can basically get a fully statically compiled HTTP.jl that you use, and then everything else is then dynamic, but that'll take a while. Yes.
So a couple of quick questions. One is, when it comes to deploying basically on GitHub through actions, do you have any specific tips or advice on that?
Not really. I mean, on that actions, you do whatever works. I don't think there's any major thing. The only important thing, I guess, is to set up caches correctly, because that'll save you a lot of time in downloading and recompiling or precompiling every time. So the critical thing, I guess, is to set up caches so that once you precompile, you have your depot, you can reuse your depot from one run to another, because that takes a while. Chris might have more tips about.
Your depot won't actually be the same between the different Julia versions. But one
No.
of the things that can help you, the biggest thing that can help you is, so Julia or GitHub Actions, their default runners are always going to give you a blank runner each time. So even if you use a lot of the caching things, there's so many different architectures and stuff you can end up getting in the cloud that they basically have to just have to be pessimistic and throw out too much of the caches. If you allow yourself to set up, just like a simple, like 404 server or something as like an internal node, it will actually cache very well. So you'll see like a lot of your task will suddenly run in like 30 seconds or 3 minutes or something, because it can keep a lot of the binaries between them. If you're doing things like PRs that are then only adding new tests or adding new benchmarks or something, it should be completely cached already, because if you just make it so that way it shares the binary caches. So I'd recommend in that scenario, the actual thing to do is just to not rely on GitHub Action servers, because the way they do the containerization is actually the thing that's killing the caches, not necessarily the rest.
All right, I guess I'll follow up with you on that to try and understand how to do this.
I can show you. I can show you what we ended up doing for ordinary DQQ, because like ordinary DQQ has 96 different tests that are run, and we had to make it so that way we cut out the pre-compilation. We only compile once, and that's how we got it.
Great, thanks. So my other question was about the Pluto package that I was surprised not to hear about, given that they were one of the innovation was to include the project and manifesto in the file. I'm wondering why, or I guess to what degree, is Julia Hub sort of promoting and supporting Pluto, or is it a bad idea, or should I forget about it?
No, Pluto is a great idea. But Pluto has nothing much to do with Julia Hub. It's run pretty independently. We support Pluto on our platform, so on Julia Hub itself, you can run Pluto, but Fonz sort of is pretty independent in doing maintaining Pluto. A lot, as you were saying, a lot of ideas from Pluto are being populated into other areas. This project and manifest in the file is obviously something Pluto started doing. That is now in PKG. I'm not certain if the two are sort of compatible, or they'll use one or the other. I don't know. That's again a question probably for Fonz or Panayotis. But yeah, Pluto's ideas are obviously being used elsewhere. Malt, which Pluto started, is also something that we use at Julia Hub now as well, to run distributed code. Malt is actually pretty great, even though I didn't talk about it. But it's a little bit of a detail, I think. But yeah, so Pluto's done a lot of great stuff, and people are using it, but I don't know anything beyond that. Just see what Fonz does and follow what he does. I think that's the message, I guess.
Fair enough. Thank you for a great talk.
Thank you.
We have a question here on. Okay, so the question that we have online is, does using Nix PKGs as a tool be useful in case of cross-compilation? I believe it has a concept of build platform and host platform.
I don't believe so. I don't know much about Nix. I don't use it, but I know a lot of people who love it. But I don't think it'll help with cross-compilation as far as I know, but that's just a very vague answer. Chris is smiling, so I think he has something to say.
Well, I'll say that there are very many... I don't know, maybe I don't want the mic for this. Nix's package management and stuff has always kind of generally given more complicated Julia packages a bit more issues, because they have different Julia build and certain things like that. So while Nix has some very great ideas, I do find that on the more complicated projects it hasn't really panned out so well. And so I wouldn't be so keen to be trying the next Nix thing, but they do have some very good ideas that we need to be pulling into our infrastructure and such. That's, I guess, how I'll say it.
Thanks, Chris. There's a question here in front, I think. Are we okay with time?
Hi.
Yeah.
Thank you. Awesome presentation. I wanted to ask you, I have a little experience working with deploying Julia within a Docker container. And one of the things you mentioned with the memory hints was really useful, because I have experienced some weird behaviors, and I think this explains it quite a bit. I have not thought about this, so thank you for that. So my question is, I've noticed that Julia can be quite intensive in size of the container.
Yes.
And also memory utilization. And I was wondering if Julia C, it might be helpful to reduce the size of the container.
Yes.
And also the memory.
Yes. So absolutely. So like we run containers which are like 8 gigs, right? And it takes 30 seconds to even download it from the AWS container registry to the node, right? And that's 30 seconds of latency that you lose in every request. So that's the problem, yes. And Julia C will help, but I am not certainly it will help anytime soon, because the reason why our containers are 8 gigs is that it basically downloads the world, right? It has maybe dependency on 1,000 packages, right? And getting all of those packages to be trim compatible is going to take at least a couple of years. So, so yes, once the ecosystem is more robust in terms of trim compatible packages, absolutely it'll help, but not, in the next few months, I think. In terms of memory, I don't think so. I think Julia's, the one thing that, sort of blows memory out is, of course, BLAST. So setting BLAST threads is one important thing in terms of, keeping your memory in check. But beyond that, the Julia compiler itself uses a little bit of memory, but not too much. So maybe there'll be some changes at the margin. My gut feel is that it won't change too much. Most Julia code that uses a lot of memory generally is just because it's doing stuff, right? And it'll keep doing stuff. It does a lot of work, and so it needs memory. So I'm not sure that Julia C will help very much with memory, but certainly on image size, it'll help once, the ecosystem is a bit more trim compatible, right? So I don't know if that answers your question, but I mean, it's feelings at this point.
Yeah,
right?
you did. Thank you. Another question
Sure.
is, how do you know any tips on, maybe we cannot mess with the memory footprint on the Julia application itself, but do you know any tricks of maybe changing some of the parameters when building a Docker container, or deploying in a Docker container, changing the memory parameters? Any tips on tricks on that to reduce a little bit the memory intensity of a Julia application?
I'm not sure, immediately if I can say much. As I said, the BLAST threads makes a big difference, right? I think the default BLAST threads are set to large, like 64 or something, and you don't really need that in a Docker container. And the memory that the BLAST uses is proportional to the number of threads that you use. So reducing the number of BLAST threads is something quite immediate that can reduce it. Beyond that, I don't know. If I think about something, I'll let you know.
Okay. Thank you very much.
Thanks. Thank you. Thanks a lot.
Thank you, Avik sir, for insightful talk. Our next speaker is Christopher M. Tessim. He is an assistant professor of civil and environmental engineering at the University of Illinois at Urbana-Champaign. His research assesses air pollution-related effects of human activity, focusing on mechanistic modeling of outdoor air pollution and its health impacts, quantifying inequalities in the distribution of those impacts, and proposing and testing solutions. He studies the relationships between emissions, human activities that cause them, and the resulting health impacts, and develops modeling capabilities to enable these types of analysis.
All right, thanks everyone. So for having me. So I'm going to be talking about equation-based geoscientific modeling and surrogate modeling. So first, some terminology. I think probably everybody already knows this, but yeah. Oh. Maybe if you go like this. And then, all right. So probably everybody knows this, but just geoscientific modeling, kind of numeric models of the Earth system and its components. I want to make a couple of points here. One is that, it's a pretty big area of science, right? I think we all know this because we're all here. But I want to put this here also because I'm going to transition really quickly here into talking about my specific area of expertise, which is air pollution. But I want to kind of keep in mind that the techniques that we're going to be talking about are pretty general and can be used in other areas of geoscience. All right, and so now I'm going to transition to air quality. And so I want to try to convince you that air pollution is important. So there's a couple of facts. One is that air pollution kills a lot of people. So it's about 5 million people per year globally, about 100,000 people per year in the United States. It's usually the largest environmental risk factor for dying. So that's one thing to keep in mind. One reason why we'd want to model it, study it. Another is that a lot of us are kind of working somewhere kind of related to climate science. And so if we're talking about climate mitigation, climate action, a lot of that is, at least in the United States, kind of comes down to air quality modeling in a kind of a weird way. And so I'll illustrate that here. So here, this is a process that's actually currently going on right now. So we have this Dominion Energy company who they're trying to they have power plants. They're trying to demolish one of them and build a newer, bigger one, I think presumably to power data centers in Virginia. And so when a power plant company wants to do something like this, they need to get an air quality permit that says that they're not going to break any, result in any laws about air pollution being broken when they build this new plant. And so they submit their application, and then there's this public review period where, in this case, they got around 4,000 public comments. And then the Department of Environmental Quality has to write this, response to it. And so here it's like a 40-page document. In this 40 pages, they have, they mention the word model 150 times, right? So it's all modeling, modeling, modeling. It's, and so this process about whether the power company can build a power plant or not comes down to this kind of model battle, right? So hopefully I've convinced you that air quality modeling is important. It's important to say kind of what's our environmental future. And the reason for that is that the air pollution laws, at least in the United States, are the ones that have teeth, right? The climate laws don't. So if this air quality modeling is important, we probably want to know what is an air quality model, right? And so when I think about it as an academic that works in this area, what an air quality model is, I usually think about something like this. So on the right side, we start with estimates of what the emissions of air pollution, different air pollutants are, and shown there. Then on the right side, so left side first, right side second, we have to bring in information about meteorology, so wind speeds, directions, mixing, radiation, things like that. And in the middle, then kind of the main thing that we do is we have this big model that shows how after the pollution is emitted, how it's kind of transported around from location to location, how it's transformed to become more or less toxic with chemical reactions, how it's removed from the atmosphere but through different processes, and ultimately how people are exposed to it. Right? So these are complicated models. They're difficult to run for a number of reasons. There's a lot of processes that need to be represented. They're computationally intensive. There's a couple other reasons that I'll get to in a second, right? But this is kind of, the work that I do, something like this, right? How if we ever go back to the model battle that I just showed you in that document, what I just showed you there, that's not what they're doing, right? So in the model battle, they're doing something like this, where they have, you have a smokestack. The emissions come out of the smokestack. They go up a little ways, and then they just go in a straight line, right? And so when we have all this effort going into, should we be allowed to build this power plant or not, it's kind of operating at this level of science, right, at the best. And that's the power plant will usually run a model or the power company will use a model like this to try to show the impacts. And then the other groups that often don't want the power plant to be built in their neighborhood will either say, well, you did this modeling wrong in some way, or they try to do their own modeling, which would be similar. But a lot of times, these kind of processes are not informed with the best science, right? And so I have I think there's a number of reasons why this is, right? I'm not going to be able to fix all of them. obviously, but I have a hypothesis about one reason why, right? And so for, the people that are engaging with this are usually going to be, environmental scientists, atmospheric scientists, geoscientists, things like that. They're usually not going to be computer scientists, right? And so geoscientists, physical scientists tend to think about the world in terms of, equations, in terms of reaction systems, things like that, right? What they don't tend to think of is something like this. So this is a seashell script, script, which is just kind of one of the things that you might use. I don't know what's going on here. Maybe try the different. One of the things that you might use to, let me see. There's a label on this that says not working properly. That's it's not a good sign.
It's supposed to be that one is working.
Okay. It's just
It's all right.
we're back. Okay. I just need to not touch it. All right, so this is, some sort of computer code. And so when you get people who are trained in environmental science, usually they're not, they're just not like able to natively interact at this level, right? I didn't touch it that time. Okay, now it's back. Okay, maybe this will work better. All right, so in general, physical scientists, a little bit more comfortable with something like this than something like this, right? And so the issue is that all these models, even the simple ones, are usually, they're implemented in some way where you have to do a lot of this kind of computer code in order to use it at all. And just a lot of physical scientists aren't able to do that. So if that's one reason what's kind of, keeping good science from really being used in these processes, then a way that we could kind of get around this, we could fix it, is by thinking differently about how we develop our models, right? So instead of typically now they'd be written in Fortran or something like that, instead we can try to write them, in terms of equations. So when you're, if a scientist that's developing a model, they'd write down, reaction systems, for example, that would go into the model, right? They write down systems of equations that would go into other components, maybe. And then information about how the different components would be coupled together by, setting different variables and different component systems equal to each other, right? And so that's what a human would do in this case. And then kind of the rest of everything that would go into model development would be happening automatically, right? So, take all your different systems of equations, couple them together, kind of simplify them into one big system of equation, generate code from that, and then do various different steps to kind of make that code more efficient and something that can run on actual hardware, right? And so that's kind of what we're working on, what I'm kind of going to show you about here. So obviously, this is not something I could do by myself. It's built, so our code that we write is called, we call it EarthSciML. It's the one in orange there. But then it's kind of built on top of and within this entire ecosystem, it's, I think, developed by some people actually in this room that know it better than I do. Feel free to tell me if I've got my arrows in between the different components all mixed up. But we think at this point we can kind of do this. So this is one example of what we can do. So here's it's a model result of predicting ozone, which is one of the chemicals that we care about. It doesn't matter too much except the fact that it does actually work. So on the right side over there, we see basically time and the concentration predictions, the average. So the blue line is the observed, so like actual measurements of ozone at the ground level, and then the red and yellow lines or red and orange lines are model predictions. So our model is kind of under-predicting at this point, but it's we're working on it. I think at this point it's something that could actually be used in certain applications that are not too dependent on accuracy. And so that's one thing we can do. We think it might be useful if it's fast enough. So we've also started to figure out how fast it's able to run. So on the left here we have what is a work precision diagram, and maybe some of you are already familiar with this. If you are, you probably will think that the axes are backwards. So usually the x and y axis would be split or be switched. But we can see here one thing that we can do that you usually can't do with normal air quality models is that we can use different methods to solve the equations. So the ones in the dotted lines up here are ones that we've kind of hacked together, kind of a normal way to solve systems of equations for an air quality model using string splitting. And then the ones with the solid lines are some of the ones from the differential equations packages using implicit, explicit methods. And so currently, the implicit, explicit methods are more accurate, but they're slower than our kind of handwritten ones. I think this is going to be a pretty typical case in geoscience modeling where there's, these models are very kind of hand-tuned and hand-optimized to work well with certain situations. But I think, with work that we can get these kind of standard methods to work be both faster and more accurate at time. And then over here, on the right side, we have information about how the runtime scales with the number of grid cells in our model, right? Ideally, we want to run the model with a lot of grid cells at high resolution. And then, so those are the lines on the top are our model. And then the ones at the bottom are a different model that I made in graduate school that does kind of a similar thing. And so you can see our new model with these equations is a little bit slower now, but it tends to scale a little bit better with the number of grid cells. And again, we think that we can probably speed this up. And we'd be obviously very interested in working and discussing with people on ways to do that. So just as a kind of example of once we have the system working, what we can do with it. So here, this is a lot of times something that you want to do, something that we showed at the very beginning. You want to make some sort of simulation about what the existing kind of business as usual type of environmental situation is, air pollution in this case, and then say how would that change if we were to change some sort of input. Right, so here we have some code to import our packages, set up a space and time domain that we want to run the model on. Kind of put together the baseline configuration components of the model that we want to run. So we have, chemistry, photolysis, like radiation, things like that, deposition. And then we add in emissions for, from kind of all the emissions of air pollutants in the United States in this case. And then we also have another scenario where we also add in a 30% reduction in emissions from cars and trucks on the road. And so we can do that with this amount of code. Then this code over here runs the model, get these results here. For you, it doesn't really matter what these results are. But kind of the key takeaway is that we can do this in something like 30 lines of code, right? And so for me, like as a graduate student, this is kind of what I did in graduate school, but with the more kind of Fortran-based models. And to do something like this, just to kind of configure the model and maybe not even run it, with a more traditional model would take like several weeks or a month for me, like now as a professor, right? So is to the extent we can get this all working, it really does streamline the process of this type of analysis. Another thing that we can do is, so there are different kind of frames of reference that can be useful in this type of modeling. So the one we have back here is where we had kind of split our domain into grid cells and track how things move in between the grid cells. Call that an Eulerian frame of reference. Another thing that sometimes we want to do is say our frame of reference is a packet of air or fluid and track that packet as it moves around through the atmosphere. And so that's called a Lagrangian frame of reference. In both cases, it's the same system of equations, but just it's in a different form. Right, and so normally, if you have your kind of Eulerian model, your Lagrangian model, there's going to be completely two separate code bases with completely separate teams working on them that don't talk to each other at all. In this case, we can just use the same model, but make kind of a slight tweak to the equations, the way they're put together, and then we get the different frame of reference. And so we can compare that to a kind of traditional model that does the same thing. We can see that we get a similar result. We believe that we should be able to get our model to run faster than the traditional one, but we're not, not quite there yet. So far I've been, so far I've been talking about what I think is kind of the main bottleneck to be able to kind of democratize, kind of streamline this environmental modeling, something that's going to be is important now. It's going to be more and more important as climate change progresses. And so in my mind, kind of the main bottleneck is just the usability of these models, right? There's another one that I think is less of a bottleneck, but is still there, which is that they're very computationally intensive, right? So what if we also want the models to run faster, so we can use them for more things, more people can use them? And so there are a number of different ways to do this. One way is just to be able to solve the systems of equations faster using kind of different, mathematical techniques. I know some of you in the room are doing great work over that, and we're very excited about it. But also in kind of parallel, one thing we've been kind of working on different machine learning techniques to do this too. So kind of our approach to this here, there's a lot of different things that you could do. But what we're working on is to try to say we have this model that has a bunch of different components in it. And we're trying to take the individual components and kind of streamline each of them to be able to run in some way faster that gives similar results. So in an air quality model, the most computationally intensive part of it by far is the part that does the atmospheric chemistry. And so what we've been working on here is we can take a kind of a complicated atmospheric chemistry model. So here we have basically we have this kind of cloud, and the dots in the cloud are the different chemical species. There are 5,000 of them. And then there's these lines that represent the reactions in between the species, which are, in this case, 15,000. And by using kind of machine learning techniques, we can represent the same system with a reaction system that instead has 6 species and 12 reactions, right? So it's much, much faster. In some cases, our machine learning model and the reference model map to each other very well. In other cases, not so well. And so we're still working on that. But one thing that we're really excited about with this is that with this system, we give a mathematical guarantee that our simulation will always run, right? It's not going to go to infinity or anything like this. And this kind of issue of runaway error propagation has been something that's really been plaguing the kind of the field of atmospheric chemistry and machine learning for a while. So we're pretty excited. We think that we've kind of solved this, at least that part of it. And so you can see here, this, as you would hope, we can get several orders of magnitude of speed up. You can see in the red line, so this is a reference model. Here we have the machine learning models and on a GPU and a CPU. You can also see that one thing here we're still working on is this is the number of latent chemical species that we use to represent our system. Ideally, you would hope that as you increase this number of species that you're kind of representing the system with, the more chemicals you have, the more accurate it's going to be, hopefully. So we are able to do that up to a point, up to 6 species, but then after that, it actually gets worse. And so we're still, we're working on that. And then over here, we can see basically, once we get to a certain point, if we're doing a bunch of simulations in parallel, like we would if we have like a big model with a lot of grid cells, at a certain point we can get good speed ups from using a GPU too. So one more thing, we're also working on doing machine learning for advection. So if the atmospheric chemistry is the most computationally intensive operator in the model, advection is the second one. So advection is where you have wind that's kind of blowing the pollution from one grid cell to another grid cell. So we're working on representing that using a convolutional neural network where we just have our concentration and the wind speed as the inputs, and then the flux from one grid cell to another grid cell as the output. A benefit of doing it this way is that we are able to get good properties with regard to mass conservation, which is important. And so here, I won't talk about it too much, but on the top here, we have this example simulation with our reference model where we have an initial condition here and then kind of how it evolves over time. And then down here, we have different machine learning models. And you can see that all of them, pretty much give the same, at least to the eye, the same spatial, pattern as our reference model. So it's working well at this point. It's actually turned out to be much more difficult than I would have thought going in. But we think we kind of have it working now. And so you can see, so this on the x-axis is like how much of a speed up we get against the baseline, and this is the accuracy up here. And so you can see this red line to start with is our reference model, right? And so what we do in order to get a speed up is that we take longer time steps when we're solving the simulation, right? And so here with our kind of traditional model, we can double the time step and actually get the same result. We can also multiply the time step by 4 and get the same result. This suggests that we just had a relatively small time step to start with. But then if we try to multiply the time step by 6, basically accuracy goes to 0 and the model doesn't really run at all. And so this is kind of a traditional what will happen when you do fluid dynamics simulations, right? If you have a time step that's too long, it just doesn't work. And so what we're able to do with the machine learning model, which is in the blue and the purple dots here, is that when we increase the time step by a certain amount and we get, it's still pretty good accuracy. And then we can do like 8 times or 12 times or 16 times or 32 times longer time steps and still have, kind of gradually degrading accuracy, right? So we can kind of get into this Pareto frontier type of situation where we can, in certain applications, maybe you don't need quite as much accuracy, and then we could get a good trade-off with speed up. And so one kind of very implementation detail that has turned out to be important here is this purple series of dots here is when we use the kind of traditional or the most commonly used machine deep learning framework in Julia called flux.jl. And so when we do that, actually, a lot of the time, our machine learning model is slower than the reference model. So it's also, it's slower and also less accurate. So that's just like not something that we could say is useful. But when we take the same neural network and re-implement it in this other framework called simple chains, which is optimized for small neural networks, then we can actually get a system that's a lot faster than the reference model, right? So we go from, just by making this implementation change, we can go from the system that's not useful at all to one that potentially can be. So one final thing that I'll talk about because of where we are. So there's kind of, in geoscience modeling, there's a lot of applications for using optimization. So we use words like, data ingestion or data, no, I can't use the word, but data assimilation, that's it. Adjoint modeling, kind of source tracking, things like that, sensitivity analysis. I guess I tried to open a web page, but it didn't let me. Can I? Okay, there it is. And so, and this is kind of something that is, people really like to do it in geoscience, but there's often not very elegant ways to do it because it's all written Fortran. So we've been working on trying to get kind of auto differentiation to go through our kind of forward model simulation. And so we don't really have good results yet, but we have this demonstration that shows that it is possible. So that's, I'm not really going to go through this, but we can go through and kind of auto differentiate and get gradients, for some sort of inputs toward an objective for like our entire model forward simulation, right? And so this is important because, let me get this open again. Because we'd really like to optimize our model to kind of improve it, tune it against Earth observation data, or satellite data in particular. Right, and so that's something that we're really interested in going forward with and be very interested in collaborating with other people here that might be doing similar types of things. So in conclusion, hopefully I've kind of shown you that this idea of taking equations, implementing our model as equations, compiling them to a model that runs, can kind of really streamline this process of environmental analysis that becomes kind of increasingly important as climate change accelerates. And that through kind of surrogate modeling, we think that we can maybe make these models faster too. I've just kind of focused on air quality so far, but a lot of the techniques here are generalizable to other areas, and we are actively working, kind of bringing together groups to try to do this. So, thanks everyone. We, have the code is online, everything. Acknowledge the members of my group. Chris in particular, we've been collaborating with him and with the Julia lab. One thing also I just want to put up here, I know a lot of us are working in different ways with different satellite data. I've as far as I know, in Julia, there's like not a really currently kind of centralized, really great efficient package for pulling the satellite data off of the internet and doing all the things that you need to do to kind of get it into a raster that you can, raster an image or whatever that you can, they can directly analyze. And so that could be kind of an area of emphasis, community work. This is something that my group is going to be working on. So if there are other people interested too, we could kind of get together. There's an example of, in PyTorch, there's a package called TorchGeo, which could kind of be as a template. So thank you.
There we go. Thanks for a very nice presentation. I was going to ask you about adjoints, but you've already addressed that. So I'm going to ask you about, I guess, two things. One is, are you also looking at doing this in 3 dimensions? Or it seems to like maybe you're working mostly in 2D.
Oh, yeah, it's definitely a 3-dimensional model. It just, by convention, in my field, we only look at the ground level. But it's the third dimension is there too. I just didn't show it.
Okay, I guess with the 3 dimensions and the adjoint piece, it starts to be quite competitive with something called geoscam.
Yep.
Is that sort of where you think you are out already, that you could use this instead of geoscam?
So the grant, a lot of this came together through a grant that we got from NASA that we were going to make a kind of an emulator of geoscam. So that's kind of our template that we've been taking it from. It's not currently competitive from geoscam because, where'd it go? Because of this, right? The accuracy is not super great at the moment, but that's definitely our target.
Great, thank you.
Thanks for the great talk. I was just wondering, when you replace the advection by the neural network, do you do something special about conservation?
Like mass conservation? Yeah, so here, so we've done a bunch of different things. Some of them work better than others. But what we're currently doing, so basically we're predicting the flux from one grid cell to another grid cell. And so when you predict that, it is by nature mass conservative, right? We do run into issues where, there's nothing here that says that the model can't make predictions of concentrations that are negative. And when you make negative predictions of concentrations, it causes all kinds of problems. So what we do is we, any negative concentration, we clip to 0. Actually, our reference model also occasionally makes negative predictions, and we do the same thing, but this machine learning one does it much more frequently. And when you get negative predictions that you clip to 0, then you get mass. You're no longer conserving mass, but it's still it works much better than it would if we didn't have that property.
Okay, thank you.
Have you thought maybe at combining this neural network with some flux limiter to try to sort of make some hybrid machine learning numerical discretization method to avoid this error of false extrema?
I've definitely told my student, the graduate student that's working on this, to do that, and I've given him a number of ideas. He's always come back and told me that idea didn't work for different ways. So if you have ideas, we're definitely. I'm not like I'm not an expert in computational fluid mechanics, so I'm definitely open to ideas.
Thank you. I'm a conventional modeler.
Yeah.
So, if you said you told that you can conserve mass, and my question is, what about concentration? Can you also produce realistic distributions of concentrations, or do we have overshoots of the concentration?
Yeah, so I guess I was using the words mass and concentration as more or less interchangeable. So I'm not completely sure if I'm going to be answering that question correctly, but basically we do a bunch of different tests that I've not really shown here. So there are a couple of issues that we do run into. One is that so you're probably familiar with a CFL number, right? So when we get, if we're using CFL numbers that are outside of the range of the CFL numbers that we train on, then we get issues there. Another issue that we see is, especially when we have the longer time steps that we're training on, we get the power spectrum of the changes in concentrations is kind of, it's dissipative, I guess. So that's kind of an issue. We're still thinking about how to deal with that.
Thank you very much.
Thanks, Christopher. Could you go to your last slide?
The one about the
with
torch.
With the provocation about the torch.
Yeah.
Great talk. I like that point as well very much. So I suggest we discuss that later at 4, expert hour. Thanks.
Thank you, Christopher, sir, for a wonderful talk. Now, I would like to invite Milan Clover. He is a NERC Independent Research Fellow at the University of Oxford. He did his postdoc at the Massachusetts Institute of Technology, working on climate model development in Julia. He started speedyweather.jl, a global atmospheric model designed as a research playground to develop prototype ideas on machine-learned representations of climate processes and computationally efficient climate models. He also worked on low-precision computing, data compression and information theory, predictability of weather and climate, and software engineering. So.
Yeah, hey, I think I'm now the last one before the coffee break, so apologies for that, but I'll try to keep it quick. I want to talk for the next minutes about interactive climate modeling. So Speedy Weather is, despite the name, actually almost like more a climate model than it's a weather model. And in terms of interactivity, I often look up to Windy because I just find it amazing that this like software that people just put up, you can do it in the browser, you can just, it just loads in the, it has the weather forecast data in it, and then you can basically just like zoom around, zoom in, roll, you can see, you can select different fields and so, and I have a vision that I want that to be a climate model where I can just say like I run it, you can press play and it runs forward and so on and so forth, and this is kind of the interactivity that I'm currently missing in climate modeling. And so basically to start, I pulled up from, actually this is October's last year, so it's from GitHub, just the statistics showing that Python is basically on track to be most popular everything, and one of the most striking metrics I find on this is the rise in the use of Jupyter notebooks in GitHub repositories, so that absolutely goes through the roof. And so I sometimes find it, if we talk about Python, I sometimes find it really useful. If you talk about Julia, I sometimes find it really useful to think about why a language like Python is actually so successful, right? So, I mean, it has a couple of years head start, okay, get that. But it actually means that Python itself was so successful despite it not being really fast, but now people got basically the speed back in by just basically making it a wrapper around some C code. But it is definitely easy, interactive, cross-platform extensions. And software stack are always the things that everyone quotes when they say, like, why do you use Python? It's like, well, I have everything there. And of course, it's used for open source. And so this is something, I mean, obviously, I'm preaching to the choir here, what we already do in Julia as well, but we don't necessarily do in the traditional climate modeling community, and this is definitely something that's lacking. Because climate models have absolutely exploded in terms of complexity over the last decades. So the first, let's say, climate model you may think of is something that was probably formulated some 130 years ago or so, where C is just a concentration of carbon dioxide, and then with some baseline concentration, there's a logarithm in there, there's a parameter in there that you can train, and then you basically get your radiative force and you know how much warmer the planet gets. Okay, cool. This is a very, very simple climate model. Since then, a lot of things have changed. So the first models were on like atmosphere and ocean, and this is what we usually consider to be the computational fluid dynamics part of it. And then people over time have added atmospheric chemistry, what we just heard about, aerosols in there, biogeochemical cycles, carbon cycles, marine ecosystem, ice sheets, sea ice, upper atmosphere. So that's really above the troposphere, stratosphere, and so on. But also things like dust, sea spray, carbon aerosols, interactive vegetation, and so on and so forth. And now there's obviously also models that even like simulate kind of human behavior in them. And so there is a massive amount of complexity in there. And I really want to distinguish this from the typical weather forecasting problem, even though a lot of climate models have been growing out of weather forecast models. How we use them is very, very different, because in weather forecasting, you essentially have a very fixed problem. You get some initial condition data, and then you press play, and you have something operational that needs to run a couple of times a day, and you have to always provide this data so that everyone has that available, and like agriculture knows this, sailors knows this, and so on and so forth. Whereas in climate modeling, we have a bit more time, so to say, and that also means that in order to understand the climate system, we do a lot of like leave one out kind of experiments, simulating counterfactual worlds, and so on and so forth. And so our need for interactivity is a very different one than compared to weather forecast models. What we actually solve are complicated equations, differential equations like this one. I just pull this up to show it's complicated. No one really has to understand this. Well, if you code it up, you do. And obviously, there's things like advection we just heard about, effects like Coriolis gravity, pressure gradient, viscous forces, conservation of mass is in there. Things like ideal gas law. If you do it in the ocean, you have a different equation of state there. And you have also like an equation for temperature. And even though this is already complicated, once you actually solve the entire climate system, this is from these equations are already missing humidity, clouds, precipitation, snow, radiation, surface fluxes, ocean, land, and so on and so forth, right? So there's a lot we have to account for. Nevertheless, if you solve these equations, and I'm just taking this here from Simone's paper from a few years ago. This is an oceanographic simulation just showing what happens if you run this on nicely efficiently on a GPU, blast the resolution really high. You already get an enormous amount of complexity in this is just the ocean. But you can clearly also see that there's a lot of processes that we need to account for and that we need to simulate that are even like left out here, right? Like all the land is gray. Right? So there's a lot happening on land that really affects us. Of course, there's also a lot happening in the ocean that affects us. And the atmosphere you don't even see because that's kind of like on top of it. And so that really shows the dimensionality of this problem. And so because there's a lot of these processes that we can't solve explicitly, so we cannot really think about these processes as falling like through the grid cell, because we have to discretize things in some way, whether you use nice little square boxes or you use something different. But there's a lot of processes in the atmosphere and the ocean. Actually also like even in more spheres, but just focusing on these. For example, in the atmosphere we have radiation, clouds, precipitation, kind of like every little symbol that you can see in this little zoom in plot there on the right. Convection, surface fluxes, turbulence, gravity waves. In the ocean, we have a lot of vertical diffusion and mixing that can't be explicitly resolved. Eddies and turbulence, you've just seen a lot of eddies, but of course, there's always a whirl within a whirl. So that's the whole dilemma of turbulence, is that it's always more turbulent if you increase the resolution. And yeah, interaction with bathymetry, because it's really difficult to resolve the bathymetry as its full roughness as it is in the real ocean. And then again, the surface fluxes communicating to atmosphere and ice and so on and so forth. So that gets enormously complicated. And so because of this complication, at some point in the last few years or so, I've realized that maybe actually our major bottleneck to better climate simulations isn't necessarily speed, but is actually interactivity and usability. And so I basically started the question like, okay, high performance computing is cool, I get it, but maybe as trying to give a little different perspective on some of the talks that we've heard earlier, I'm not sure that it's actually always the bottleneck to faster climate research and faster climate like knowledge that we gain about the climate system. And so basically asking the question of like, how do we actually accelerate climate research? Do we just get a bigger computer? Is that really going to help us? Or do we build our software in a different way to make, to basically come quicker to solutions where then computing is not necessarily the bottleneck? And so going back in time, 1984, I think one of the first ocean models uses a so-called, in Fortran always called the name list. So there's a bunch of parameters in there. It's a text file, and then if you want your simulation to run somehow differently, you would basically just go in and just delete the text and write something else in there, and then you basically just like on your compiled model you press play, and then it would read those parameters in and compute this stuff. And so while this is somehow an easy interface, and I guess it's a fairly maintainable, maybe even interface, it really creates a situation where you can only change what the developer wants you to change. And I think this is, in weather forecasting, might be fine, because you can simply say like, well, I want to run a simulation from today, or I want to run a simulation from tomorrow, but everything else is kind of static. However, in climate modeling, because we have to understand so many parts about the climate system, leaving things out, simulating counterfactual worlds, and so on and so forth, we do end up in the situation that we have to be able to do the things that the developers don't want us to do. And so the old school models, I would summarize them as like, cool, we have the speed, great, they've been developed for decades with like tons of people, so we have the physical accuracy. They are doing a great job, but often they're not cross-platform. It like requires many people to somehow make them run on different supercomputers. Simply using it and putting another extension in it, also very difficult. Many of them are not even like properly open source, and they're definitely not easy and interactive to use. And so this is, I think, where we definitely want to, with interactive climate modeling, we definitely want to tick all those boxes. And so with the monolithic interface, or sometimes like this, it's kind of like thinking about you as being a user. You have the name list, you can press play, and then you run your simulation. It's kind of like sitting in a plane. You're the pilot, but it basically required a whole horde of engineers that actually builds you all these buttons, and then you can use the buttons, but you can't change the plane. And so sure, we're not on the side, like at least with climate modeling, we're not necessarily concerned about all the safety aspects. What would happen if you were like halfway through flying, you would like change out your engine and you want to do something else. But this is exactly what we want to do in climate modeling, right? We want to sit in the plane, and sure, we want to use our knobs, but we also basically halfway through the flight, we want to say like, cool, what happens if I now use, I don't know, winglets, or I don't use winglets or so, right? And this is exactly the things that with a monolithic interface you can't do. Monolithic doesn't necessarily mean that it's not interactive. One of my favorite simple climate models is the En-ROADS. It's also just a website, maybe you know this, where you have a bunch of buttons at the bottom. So you can say, for example, I want to have a lot of carbon dioxide removal, like nature-based, technological. You just ramp this up, ramp this down, and it actually solves a bunch of differential equations in your browser, and then you immediately see how the climate system reacts. So this is super cool. I love the interactivity. It can be used greatly for teaching and so on. But again, we're in a situation where you can only change the things that the developer wants you to change, right? Because you don't have a hackable interface. You just have an interface where you have an existing button and you can change the button, and that's it. And so to summarize this, climate models are really used for, and this is in distinction to weather forecast models. Yes, there are some repeated workflows that we have, like running certain scenarios, like worst case scenario, how bad could it be with climate change? Sure, there's a lot of high-performance computing benchmarks where you run the same stuff over and over again, as we also had a request basically earlier this morning. But there's also a lot of scientific one-off experiments, simulating counterfactual worlds, coming quickly up with an idea of like, you want to change this in this climate system, what would happen if a hurricane doesn't produce any rain? And you can basically see what it does to it. And all of these things are completely like counterfactual worlds, and so you really have to have interactivity to make that efficient. And just having a bigger computer doesn't necessarily help there. However, and I think it's always important to highlight the other side of it. So the advantage of a monolithic interface instead is really like having a simpler interface, right? You know exactly which buttons can be touched. It's definitely easier to design because you just say like, well, here are some buttons, use them. Providing a hackable interface that still like withstands all your crazy ideas is definitely a much harder one. And of course, then therefore, if you build I don't want to sit in a plane where you could be engineer and pilot at the same time. Of course, definitely not. But as long as we're not concerned that much about safety, I think that's, the monolithic interface is definitely not a way to go. And this is, I think, the important part, is that we are part of an open source community. Open source really lives from also just occasional contributors. And so we really want to tear down these walls between being a developer and being a user. If you create a monolithic interface, you're often creating a division between the two. And so definitely with climate modeling, with the interactive climate modeling, what we want to do is have a slippery slope so that every user can quickly become a developer. So we are kind of experimenting with these ideas with a package called Speedy Weather. Our tagline is play climate modeling like it's Lego. And so here's just like some videos that show you what Speedy Weather can do. There's here a global map of, maybe you can identify, I think there's, if my mouse can see here, this is, for example, then the Andes in South America, North America here. So this is some humidity. My favorite quote here is a colleague of mine, Pierluigi Vidale, wrote me at some point an email, like late at night, like unthinkable on such a small laptop, like playing a video game. And I think this is exactly what I want to get across. I want to have a model that is so fun that you can play it like a video game. So a simulation of cloud cover here, and in Speedy Weather you can also put particles in. So we heard the air quality simulations earlier. It's kind of the idea that you basically just put some particles in it, and you can just say like let the particles follow the wind, and then they just kind of fly around. That's exactly what it does. The kind of play climate modeling like it's Lego really comes from the idea that we do want to have, in the end, different building blocks and can put them together. Once you have these building blocks, you can also use just a Speedy Weather demo where we put everything into a Pluto notebook and then simply said like, well, let's choose some parameters. So you can basically, even though you have a hackable interface, you can then put a monolithic interface on top again, me creating some sliders. And the sliders are then, I mean, there's some hidden code here that says what the other ones are, like the two parameters that are here that are basically then directly used in the code below. And you can just basically then play around with them, and you see like I'm changing the resolution here and I'm changing the forcing parameter, and then a very idealized simulation here is just changing and immediately uses like Markey, and you can therefore kind of like very interactively optimize, oh, I want a bit more like this, I want a bit more like this, which is often, obviously, is not necessarily an objective way of optimizing a model, but it's often a very good start point to have an idea of what's happening. And having this in a quick way is obviously something that's super good. And so I believe with Speedy Weather, where are we? In terms of speed on a laptop, I think we're pretty good. We have the GPU version up and running, but I put it in orange here because, like, in terms of performance, it's still a bit more work needed there. But it's definitely cross-platform. Like students install it in like 2 minutes on a Windows laptop. That doesn't cause any problems. I'll show you some examples now how it's like, how it can also have easy extensions, how it's easy and interactive. I mean, the interactivity you can already see on the right. And some of the things, how we want to tackle physical accuracy, especially through the integration of machine learning into this model. Speedy Weather is actually monorepo, where we took a good amount of inspirations from other monorepos that are also developed here in the room, so for example, Markey. And so we have like Speedy Weather internals. I guess many packages have like a core package or base package or so. And then we have several packages on top of it. They all sit in the same repository. So lower triangular arrays is basically an n-dimensional version of for like representing the spherical harmonics. that we use to represent the spectral space of our model, as well as then ring grids is the package that we use for representing data on the sphere, which I guess is also relevant for a lot of people here in the room. And then transforming between the two, we have the Speedy Transforms package, and then Speedy Weather imports all of them. And so for ring grids, I thought I'd talk a little bit about it. So this is just an animation where I recorded myself playing. You see my mouse there, kind of like zooming around. This is just a HeelPix grid visualized with GLMarchy and GeoMarchy. And so ring grids basically provides you this interface. It's just something that you wrap around an abstract array. And it kind of just encodes for the first dimension where a grid cell is on the globe. But it's array agnostic, so you can put in, of course, a Julia array, but you can also put in any kind of GPU array. You can put other things in it. And then the kind of like the second to end dimension are not further specified, so you can do basically whatever you want with them. And so we have things like the HeelPix grid implemented. We have also developed a new one, an octa HeelPix grid, which is a little simpler. So they're equal area, and I'll talk a little bit about them further. But especially we had to basically also build the whole thing with this being array agnostic so that the whole thing becomes GPU ready, so that you can really just say like architecture equals GPU, and then you can use the same grids representing, for example, CUDA arrays. Maybe that's also something interesting for people here in the room. A lot of these grids are actually hierarchical, so that's something we worked on. So instead of just indexing the entire matrix by, for example, like an I, J, or as a continuous index here with this ring order, where's my cursor here? You see it goes like 1, 2, 3, 4, 5, and goes like a ring around the globe, which is super important for the transforms. But actually having a nested order can be sometimes really, really useful. So a 1, 2, 3, 4, so it feels like a space-filling curve. But it actually is in a way that it's hierarchical. So kind of changing the resolution becomes trivial because you just have to average 4 consecutive points in memory. Or you just have to duplicate them 4 times, and then you go to like twice higher resolution or twice lower resolution, and therefore I hope that at some point the octa HeelPix grid might be something which is really nice then, where we have basically equal array, efficient spectral transform, hierarchical, and everything is just one big square matrix in one go. Simona always complains about that these are not orthogonal grids, but like this is some details, but definitely we've been working on some of these things because we use them in order to represent our data inside Speedy Weather. At some point, and this is kind of looping back to what I said in the beginning, I would like Speedy Weather to basically have kind of like look like Windy, where you just say like I run the simulation, you can zoom around, you can look into, you could then like change the different fields. I want to look at sea ice now, I want to look at land and so on. That would be super cool. Or just say like I want to run the simulation for another 10 days and you see how it evolves then. So these things at some point to be added, maybe next year you'll see a play button in this one, that would be great. But otherwise this is just an existing GeoMarchy, GLMarchy, where I just have some field that was simulated by Speedy Weather, plotting the polygons. So this is also thanks to some work that Anshul did, just plotting the polygons, so there's actually no interpolation involved. It's just every field just has a color as a polygon, and they're basically all just put together with some coastlines on top for orientation. Exactly, the whole idea around modularity, flexibility, shown here again as a Pluto notebook, is super important. You see, I'm basically just literally say using Speedy Weather and GLMarchy, I'm creating the grid that just defines the resolution. I'm creating the model in the next line, and in that model I can say like convection, I can switch on and off convection, so different physical parameters. Surface humidity, I can switch that on and off or change the values of this. And I literally just initialize the model and run the simulation, and it happens in your notebook. And if we go back to the beginning, you see then basically how quickly everything updates, and it really lets you allow to play with it. But of course, and this is the important point for it, it is hackable. So you could, in every point in between those lines, you could always insert your own piece of code. And so you not have a predefined user interface. And so that was really important for us. I go through a couple of more examples. This is some work that one of my students, Greg Monday, pulled off in I think a day or 2 or so, where he just included surface roughness as learned through a neural network inside Speedy Weather. So surface roughness is basically, you need to know this in a climate model because whatever your surface fluxes depend on how much turbulence there is, right? So if there's a lot of turbulence, like you can warm up the atmosphere quite quickly, or the flux goes the other way around. But the surface roughness is very different if you have a very calm ocean, if you have sea ice on top, or if you have rough ocean waves, or on land, whether you have like little grass or big trees. And so there's basically this surface roughness is usually something that we would load in from data, but we said like, well, we want to have a climate model. Why don't we just like try to learn this? And so just has learned this. He literally just used just a PyTorch model, and then we just load this in as a first step. Of course, at some point, we would love to do this more efficiently with Lux or so, but it clearly learned that there's, for example, no trees in the Sahara, that it actually needs to have a higher drag coefficient through the higher surface roughness where there's a lot of trees, so like in Central Africa, but also in like Siberia, or in like Canada up here in the Amazon and so on, and then other areas are lower surface roughness and therefore a lower boundary layer drag coefficient. That's what you see in the top, and then the bottom what we just had before, where I literally just picked two values. I said like, well, on average, surface roughness is maybe like this over land and like this over the ocean, and obviously does a much better job. And this this is something that we really, what we built Speedy Weather for. Is not like we want to throw the entire climate model away and just learn everything from data. No, we want to plug in a lot of small neural networks into different parts so that always the inputs and the outputs have some kind of physical meaning. Therefore, we get rid of this whole idea of the internals of the learned climate model being a black box. And if we have a lot of small neural networks, we can basically really like design it in a way that respects a lot of the physics. And this is kind of what I believe is really cool here, and it would even support generalization, so you could move your continents around and you would still have it, and you don't need to load it newly from data and so on. This is one point I touched on earlier. I guess like the name Speedy Weather is almost like a bit, it's not inclusive enough now. Maybe we should call it Speedy Climate at some point. I guess that's not going to happen, but just to show you, we now have also a slab ocean model. So it's basically an ocean model where you just set all the velocity to 0, and a thermodynamic sea ice model, which I just showed here in the video. So it's a super simple sea ice model, but it basically does kind of okay job for given the simplicity. It's just like a few equations, but it nicely grows the sea ice in the respective winter hemisphere on either hemisphere, and also have a land bucket model so that it simulates like temperature, humidity, snow. So snow can be produced, falls down, and so on. And so the whole thing really becomes more as like an atmospheric model with simple representations of all the other spheres, and that was important for us. For the GPU stuff, and this is basically the last point I want to make before your coffee break, is that one thing I'm very proud of is like recent developments on the GPU stuff, where a lot of the parameterizations are written in a way that they can super easily be executed on the CPU as well as on the GPU without any code change. And so these few lines are basically how the albedo is calculated over the ocean using sea ice. In the end, it is a relatively easy formula, but we've written the whole code so that actually everything is quite self-contained. So you basically, if you want to implement a new thing, you literally just write top to bottom in one file some code, and you don't have to jump across different files and change different things here and there, which is obviously something that we realized is super important if you want to let your like model development scale. If you want to implement something new and you suddenly have to touch 500 different things, that's going to slow you down. That's going to like cause a lot of merge conflicts and so on and so forth. If you are able to write a new component that really just like reads basically top to bottom. So really this has like kind of like it has the doc strings in it, it has all the default values in it, it has one line that's important for the GPU code, like how to adapt this for so that the whole struct can be on the GPU. It has like the user interface as a constructor in it. It says like what to do when it's initialized, nothing. And also what actually needs to be done when it's computed, with a couple of, there's like a hash key that's actually compiled away and so on. And so this whole code can be executed on CPU or GPU. And you can, and I want to show this as a contrast to, maybe some of you have heard a couple of weeks ago, a month ago maybe, was the Gordon Bell Prize was given to a Fortran climate model. The Gordon Bell Prize for Climate Modeling 2025 went to ICON. And ICON is this like, okay, massively big model, everything has been developed, but there's one part in their paper that was then published in, what is it, one of the journals with this Gordon Bell Prize, and they basically talk about how they've written some of the kernels. And what absolutely struck me was like to see that actually A, it's completely unreadable. B, the lines of code that actually do things are fairly little compared to all of the lines of code that have to be added in order to get all sorts of like OpenACC, GPU statements in there. And so they really took this approach of like, there's an old school Fortran model, there's a loop, and I'm basically just like peppering around some kind of lines of code in order to tell the GPU compiler what to do with this line of code. And so what I think is a massive disadvantage of like, suddenly you basically have intertwined lines that are responsible for like the scientist writing the actual like algorithm, and then what they call performance engineer, and you kind of have to, but they kind of just turned this around and said like, we have a separation of concerns, and I think it's kind of not actually this, because you're conflicting two roles completely in the same code base. And so writing code where actually less than 50% are actually describing the calculation, I'm not sure that's the right thing to do. So I hope that we can write climate models that are better than that. Don't quote me on this. Thanks. Questions? Yes, that's one.
Now I'm being hated by everyone. Thank you very much for a wonderful presentation. My question is, you had question marks on the physical accuracy about the speedy weather. So my question is if in speedy weather someone can actually play around with the equations, the differential equations that you're using, or is if this off the books and you're just not supposed to touch that? Thank you.
No, so you definitely can, but I'm hesitating a little bit because there are certain things that are a little bit more hard-coded than others. So with all the, like in an atmospheric model, a lot of emphasis goes to the parameterizations. So all of these unresolved physical processes, radiation, convection, precipitation, and so on. Those ones you can always like swap out, switch on and off, that's no problem. In the dynamical core, so that would actually solve your primitive equations that I've shown earlier, there is definitely a few of these terms you can just like switch off, you could change, but it's not as modular as, for example, like Oceananigans, for example, has the idea like you can run it in like a little square box, you can put your whole grid around the globe. Because of the numerical approach that we've taken, we're basically hard-coded to a sphere, so you have to always use a sphere. There are also obviously other, maybe you've ever played around with the Daedalus model in Python, which is super cool because you can basically just write, normal, like you can write your equations as like a string and it would translate that into code, and therefore you can basically execute any kind of operator, even though basically but like just chaining things together. We're not quite there in terms of the flexibility. So the idea is still that this is a model that should always solve a certain set of equations on the sphere. But there is some flexibility of like tweaking those. You couldn't do everything, but you can still do a lot on the dynamical equations. But the emphasis is really on like the climate processes, so that they can always be super flexible, be switched in and out. Go ahead.
Yeah, I guess I'm kind of wondering, on a couple of levels. One, so this speedy weather is a simplified, heavily parameterized atmospheric model. To go from that to a full climate model is a gigantic task, one that the climate program sort of, ambition to do, and has had a lot of, time, manpower, funding, and developers involved in, and they are, and they are relatively far from their goal. Mm-hmm. So I guess I'm slightly uneasy about the notion that it's just about, switching to a different language that is an interactivity that's going to sort of get us there. I love the fact that all of this interactivity comes directly from Pluto and Maki and Julia itself, and I'm totally on board with that. We've talked about this before in JuliaCon and others, but my question really is about, I'm always concerned with the ability for users to sort of break consistency within a model. Like a scenario whereby somebody takes speedy weather, puts a few factor of 2 or 3 here and there because they decided this was smarter, call it speedy weather, write a paper, never contribute their code back, and kind of how do we, as a community, deal with this kind of, I guess, inopportune development?
So you're basically saying that if you were to write code that is so hard to use that you always need the main developer, then the information of a new development can't bypass the main developer. Whereas if you produce something that's like super easy to use, people can run away with it more easily. Is that?
No, that's not what I said. You could break a Fortran model just as well. Right? Yeah. I guess it's not the interactivity to me that leads to better science. It's the reproductivity more so, and the checking on what the actual code does. And that is a difficult undertaking. One that has nothing to do with the use of text files, interactivity, or even our ability to bridge between users and developers. I'm sometimes worried about, I guess, scientific reproducibility is my question is about. How do you think about speedy weather in this context?
Yeah. I guess like a lot of what you basically mentioned, a lot of reproducibility comes from the fact that you can use it in many different ways, right? You can just like what basically shenanigans engineered is like this idea that you don't have a name list anymore. You have like a script that basically just defines your whole thing top to bottom. So actually reproducing the exact same simulation is like, I mean, that's fine. Actually knowing what exactly executed, and if you, because it's such a complex system, and you just want to do an experiment kind of touching in one corner, making sure that this, what you're doing there is actually consistent with everything else, is, I'm not sure whether there is a general easy way to kind of solve this. What I think at the moment, as like probably the best approach, if you make something really usable for someone, then they can go out and implement it. But then what I think is the best approach is to just kind of like, let's say, open an issue and let us know about it, what you did. And then we can kind of verify like, yes, that's kind of like how we would have done it too. Because of course, there's a lot of knowledge that you can't just all write down into documentation. It's very difficult to kind of like make something easy, but not leave out all the details. And I guess there is a discrepancy here. But at the moment, I think it is the best way is to like start easy, get your stuff implemented, and then kind of just ask for review from the people that wrote more about the code. But I'm not sure whether this is the best approach. It's a good question. Any last question? Coffee break. Coffee break. Good. Thanks.
Thank you, Milan sir, for a great talk. Now we have a coffee session for another half an hour. We will gather here again at 3:45.
Aprenderam mais coisas sobre o Júlio. Não foi tanto código. Não foi tanto código.
Que horas é que vamos estar aqui?
Não, mas também vai ver
Em dois. O seu espanhol.